Hello. Can you hear me all right?
Yeah.
Cool. Welcome to this week's London Learning Lean seminar. Next week we're going to be hearing from Janae and Bayek talking about the Erdos-Tuzer-Vultra conjecture. But this week we're very excited to welcome Ella Yu from Imperial College London and Xiang Li from Cambridge to talk about formalizing some results regarding Euler's Totient function and the prime number theorem. Over to you.
Hello everyone, I'm Ella, and I'm gonna start to share my screen now. Okay, can you guys see the screen?
Yeah.
Okay, so I'm gonna start now. Today, Xiang and I are gonna talk about Euler's Totient theorem and a part of the proof of prime number theorem. So I'll start by talking about Euler's Totient theorem. I'll first remind you guys about the Euler function phi of n, which is defined to be the number of natural numbers not exceeding n, which are co-prime with n. And for phi of 1, we have phi of 1 equals to 1. And the Euler's theorem is stating that for every natural number greater than 1, we can have here an equation, a to the power of phi n minus 1 should equals to 0, considered in mod n. So this is the theorem, and I'm gonna first talk about the mathematical proof of it. We can first consider the ring Zn, which for every integer I will denote the coset of I in Zn by I. Then this problem can change from the proving the equality we talked about before to proving this equality, a to the phi n equals to 1, if we consider it both of it in the coset of I in Zn. Then we can consider all of the co-prime numbers not exceeding n, which are k1 to k phi n, since there are phi n of them. And then we can list them as this, from k1 to k phi n. And these k1 to k phi n can form phi n coset groups in Zn. And we claim that if we multiply each of it by a, then these k1 times a, k2 times a to k phi n times a are the same elements of ring Zn, but possibly in different orders. So since these are two equal sets, we can have the following equality of the product. So the product of k1 to k phi n should equals to k1 times n to k phi n times a, k1 times a to k phi n times a. And then we can extract each a out, and since there are phi n of them, we can have a to the power of phi n. Then we can cancel out the k1 to k phi n from both sides and get the equality. So this is the mathematical proof that I'm going to follow, and then I'll introduce how to formalize this in Lean. Okay, can you guys see the codes now? Is it clear?
No, it's still the slides.
Okay, I'll start the screen sharing again.
Yeah, yes, I can see you now.
Okay. Okay. Sorry. I think there's a bit that sorry. Okay, so this is the math proof that I'm going to follow, and to formalize it in Lean, we'll break down the proofs into 3 parts. So we can see that in the proof that we mentioned before, there are 2 products, m equals to k1 to k phi n, and n equals to k1 times a to k phi n times a. And the first part of our proof will be to prove that these 2 big products are equal. And then we want to take out the term a to the phi n, and then we'll cancel out the m here, which will give us the result. Okay, and now I'm going to show the code. Sorry, I think my screen is freezing. Can you guys see the codes now?
No.
Okay. Sorry, I think my Zoom is not working. Well, now I need to re-enter the room, if that's okay. Oh, sorry, it's still loading.
Yes, by the meanwhile, Ella, is it okay to share the link of the GitHub project of our project? I think it's convenient for the audience, to check the codes later.
Okay, I think I will share it after this talk.
Okay.
Sorry, I'm not sure why this sharing isn't working. I'm trying to share my desktop. I'll quit the meeting now and then rejoin it. think it's working this time. Can you see the codes now?
Yeah.
Okay, nice. So first, I'm going to prove that, how can we show two products are equal. So here, we'll have a sublemma called same product condition, and we need, these are the conditions that we need. We need two functions, which are from alpha to a common monoid M, and then we need two hypotheses. One is that the set range of Q is a subset of the set range of P. And the second condition is that this function Q is injective. And if we have that, we can show that the products of the range of these two maps are equal. Okay, so to show this, we can use the product bijective lemma, which is already in MathLib. And to use that, we need to have the following. We need to have a map E from the domain alpha to alpha and two hypotheses. The first one is that this map E is bijective. And second is that for every x, we can have that f of x is, there exists a g of E of x, which equals to f of x. Okay. And so for the first part of the proof, we need to first show that such, for every I in alpha, there exists an j in alpha that qi equals to pj. And this can simply be shown by having some lemmas in MathLib about the elements, the members of the range. And next, since we are not quite sure about how the map E works from alpha to alpha, we'll just need to show that this map is mapping non-empty things. So we want here a non-empty condition, which is stating that for every I in alpha, the set that the corresponding pj that equals to qi, the set is non-empty. Since we already proved that there exists such j in alpha before, we can state here that it's non-empty. And having this non-empty condition, we can build the map E, which is alpha lambda I, and it maps to the set non-empty dot sum, and using this non-empty condition. So this E is an arbitrary map that tells us that it maps I to some non-empty set. And now we can define the EI as follows. So EI should belongs to the set, a set of PJ that PJ equals to QI here. And then we want to show the last condition we mentioned here, which is that for every x, we have f of x equals to GEX. And here it will be for every I in alpha, we have QI equals to PEI. And this is exactly our definition for EI. And finally, to use the injectiveness to show that this E is injective, we want to have the we will need to use this H-comp hypothesis here, and we'll use this H-comp condition here to build two different maps. EI and EJ. And then since we can show that EI and EJ are if we rewrite this EE condition and then rewrite EJ at EI, we can show that they're exactly the same, which tells us that this function E should be injective. And then we can use this injective condition to show that this map is bijective, which finish our proof of the product of bijectiveness. And this lemma will be used in our following proof, which in our proof, the maps from alpha here, alpha will be our set of coprimes. So this should be the set which for each n, there will be phi n elements in this set of coprimes. And the common monoid M here will be Z mod n. And PQ will be two functions that we will define later. And now we can introduce our Euler's Totient theorem, which here we'll have the condition that A is greater than 0 and N is also greater than 0. And A and N should be coprime to each other. And we want to prove that A to the phi N should equals to 1 if we consider it in mod N. So for the first step, we want to change this equation into the form of cosets, which we'll use a lemma here called Z mod dot eq if and only if mod eq dot net, which we can see that it will change the goal to proving A to the n quotient equals to 1. And this arrow means the coercion here, which should be the square brackets if we want to write it mathematically. And so our first step of the proof will be proving M and N, which are the two products that we mentioned before, are equal. So first we need to define the set of coprimes as this, which here it is the set of X and Z mod N, which will use the X del val map here. X del val is a coerced map which maps each Z mod N to N. So we can see that actually for every val A should be less than N, since it's mapping Z mod N to natural numbers. And we can have a lemma about the cardinality of set of coprime. Since for every since the function phi n is defined to be the number of coprimes that not exceeding n, phi n is actually the cardinality of this set of coprime, and we can prove this using some lemma about the Z mod properties. And next, we'll define two maps so that we can use these two maps to build our conditions for to show that the two products are equal. So the first map we'll call this P mod, and this will be this should give us K1 to K phi n. And next we'll build a map called Q mod, which will have A times K1 to A times K phi n. And these two Q mod, P mod def and Q mod def are just functions, maps that defines in different ways so that it will be helpful for us to prove some lemmas later. Okay, so then our two products M and N can be defined as follows. So the product M should be the product of P mod J for J instead of coprime, and N will be Q mod J for J instead of coprime. And our next step will be to prove that M and N are the same. So to prove this, we need to use the same prod condition that we mentioned before. And the two hypotheses that we need to use to show these products are equal are a sub-prod condition, which is proving that the set range Q mod is a subset of set range P mod. And the second condition should be proving that this Q mod map is injective. So to prove this, we'll prove some properties of A and coprime numbers. Well, first show that A has an inverse and show that coprimes are invertible, so that here we can show that X is invertible and AX is invertible. And using this invertible condition, we can convert our A times AZ mod N, XZ mod N, without coprime N to sorry, it's loading. So using these invertible conditions, we can show that the range of Q mod is a subset of range P mod. And then sort of rewriting our function P mod and Q mod, P mod and Q mod in P mod def and Q mod def, and use the same image condition, we can show that the map Q mod is injective. So having these two conditions, we are able to prove that M and N are equal. The products M and N are equal. And our next step will be to take out each term A in the term of Q mod, and then multiply them together to get A to the power of phi n, to take out the term A to the power of phi n and get the equation M times A to the power of phi n should equals to N. And for this step, we just need to have some sublemmas of to change the to take out the terms in each product, and yeah. Okay, so I won't explain these prop change lemmas in detail, since they are just some implementation of Lean. And having these, we can rewrite our rewrite our a to the phi n into the function of a z mod n j, which j are the number of which j are in set of coprimes, and since there are phi n of them, we can take it out and then get that a to the z mod n, a z mod n to the power of phi n should equals to this a power torsion, which we defined as the product here. And by rewriting this, we will get that this m equals to, we will get this hypothesis H2. And now after we get this H2, we can cancel m on both sides and get our result. And to cancel this m, we need to show that it has unit and then show that it has inverse. And this condition of has unit is shown by a lemma called prod induction, which is basically showing that this property of has unit is multiplicative. And yes, after we have that m has after we shown that m has an inverse, we can case this m has inv in this hypothesis H3, and then sort of rewriting some lemmas of Mal-Asog, we can prove this H3, and this H3 will be our goal. So this finished the proof of Euler's theorem. Okay. Next, I'll talk about prime number theorem. So prime number theorem is stating that we need to first have a function pi of x, which is a prime counting function that counts the number of primes less than or equal to x. And the theorem is stating that we have an asymptotic formula pi x x log x, which is equivalent to saying that for every C1 less than 1 and C2 greater than 1, we can have the following inequality. So the outlines, it says this proof is very long. I will only talk about the outline of this proof. And so this prime number theorem can be proved by showing a sequence of these three functions. The first function is the Riemann zeta function. And the second one is phi of s, which has this log p we'll use, and theta x, which is log p and for p less than or equal to x. And so we'll follow Newman's proof, which he first reduced the theorem pi x x log x to showing that theta x is asymptotic to x, and the next step is to show that this formula can be reduced to showing the integral. This integral is convergent, and then after proving an analytic theorem, which we'll talk about later, we can apply this theorem on this integral I, and then to prove this theorem, it suffices to show that the Riemann zeta function is non-zero for every s that the real part of s is 1. So here in our projects, we only have time to focus on the first part and the third part. So I'll introduce how we can reduce the proof from pi x log x to showing this theta x, and then Xiang Li will talked about the third part, which is proving the analytic theorem. So for the first reduction, we can first have an upper bound of theta x by writing out this theta x, and then taking out this log p to left hand side and let it be an x. Since every x is greater than p, this theta x must be less than or equal to log x times this pi x. So we can first have an upper bound that theta x is less than or equal to pi x log x. And next, we'll have a lower bound. To have the lower bound, we need to consider epsilon, which is greater than 0 and less than or equal to a half. And we'll have that this theta x is greater than having another lower bound for p, which is changing this summation to p greater than x to the 1 minus epsilon and less than or equal to x log p, and then taking out the 1 minus epsilon and log x to the left hand side, we can get that this theta x is actually greater than or equal to 1 minus epsilon times pi x minus pi of x to the 1 minus epsilon times log x. So this second term here is just the summation right here. So combining these two bounds, we can have that theta x is bounded by this function on the left-hand side and pi x log x. And then recall that we have a lemma for Chebyshev's bounds, which is stating that for every for sufficiently large x, there exists constant a and b, so that pi x is bounded by a x over log x and b x over log x. And using this to our function pi of x to the power of 1 minus epsilon, we can know that this pi x to the 1 minus epsilon is less than or equal to this term. And then taking this x to the power of 1 minus epsilon to the left-hand side, we can get that it's smaller than 2b times x to the 1 minus epsilon over log x. And then substitute this inequality for pi x to the 1 minus epsilon back to our bounds here. We can get that theta x, we can get that 1 minus epsilon times pi x is actually smaller than pi x minus pi x to the 1 minus epsilon, and then substitute back to our lower bounds. We'll get that 1 minus epsilon squared times pi x log x is a lower bound for theta x. And dividing x on both lower bounds and upper bounds, we can get that pi x is asymptotic to x log x. So this is our first part of reduction. And now I'll talk about how to formalize this first part of reduction in Lin. Okay, so here we used some results that has been proved in Thomas Bloom's projects of unit fractions, and we use some of the results that he has in the basic estimates document. First, we'll use this pi in this Lean code, which pi refers to the prime counting functions. And since this prime counting function is defined in MATLAB in a way that is hard to be connected to our theta functions, we are gonna prove a lemma called pi def to state it in a different way. So we want to first show that this pi in Lean is equal to the sum of n, which n is in the thin set range x plus x, the floor function of x plus 1, and has the filter net prime, and the summation is taken for 1. So this condition here is basically saying that a is less than or equal to x for every real number x. And this lemma is proved using a definition defined in basic estimates called prime symmetry. And in Thomas Bloom's project, he actually proved that this prime symmetry function is equals to pi x. So we just need to prove that this prime symmetry function is equal to our function with thin set range. This is running a bit slow. I'll talk about it straight away. So this prime symmetry function, maybe I can find it here. Is defined as follows, which n is taken in thin set ICC, which ICC is the interval which has closed bounds on both sides, and then filter net prime a n. The reason why I want to use range x plus 1 here is that theta x is defined using the thin set range. So it will be easier for us if we unify these two definitions. Okay. So next we'll talk about our theta function. Not sure why this info view is not working here. But here we can see that our theta upper bound function is stating that this theta x is less than or equal to pi x times log x. And then, okay. Okay, maybe I'll continue anyway. So we can prove this bound by having, by written out this theta x and pi x using the floor function. And then if we change and rewrite this using the log property here, we can, it can be simply proved by using inequalities properties, the transitivity of inequality properties. And the lower bound is the part that is harder to prove. To prove that, we'll first prove a condition called range sub-eq IOC, which is saying that this if we have two sums which with filter net prime that is range minus another range, it is equal to this sum taken over fin set IOC A, B, which A and B are the fin set range that we used before. And this will be useful since in our proof for lower bound, sometimes we'll have the lemmas are used for intervals and sometimes it's for the range, is used for the fin set range. And here we want to prove this using the properties of set difference. And there's a lemma here that is hard to prove and we have not resolved the problem yet, which is taking the set difference, which is showing that if we can take this set difference inside the filter net prime, it should be equal to taking the first, it should be equals to first, should be equal to the set difference of the sets which we take the filter prime independently. But we have not proved this yet. But if we can have this lemma, we can then show our theta lower bounds. For that theta lower bounds, we need two hypotheses. One is that for our epsilon, real number epsilon, our epsilon should be greater than 1 and smaller and less than half, and x should be greater than 1. And we want to show that this 1 minus epsilon times pi x minus pi x to the 1 minus epsilon times log x should be equal to theta x. And then the main steps of these proofs are breaking down these inequalities in two parts. So the first part is to show that for p being taken from x to the 1 minus epsilon to x and log p over this term log x times 1 minus epsilon is less than this term, this summation, which we just which is taken by ignoring the lower bound of p. So this inequality should be easily proved using properties of division. And next inequality, we can have that this P taken over these with these two bounds for one should be less than or equals to this summation, but for log P over log X times 1 minus epsilon, and connecting these two inequalities, we can get the lower bounds that we want. Okay, and the Chebyshev lower bound and upper bound are being proved in Thomas Bloom's projects of unit fractions, but we have not yet connect these Chebyshev's bound to our two bounds for theta function yet. And that's our progress on the first part of reduction. And Xiang now will introduce the second part, which is about analytic theorem.
Sorry. Can you see my screen?
Yes.
Okay. May I ask first how much time I have?
I mean, technically about 15 minutes, but you can go over if you want.
Okay. I will do as fast as possible. Okay. So, yes, as Ella previously said, my work is doing the analytic theorem, but actually I'm not, because it is more complicated than I thought. So actually, I focused on the Cauchy's integral formula. So because to prove the analytic theorem, we have to construct a contour, a rectangular path, and we make the rectangle expand to infinity, and then we can argue this result. But due to the time limit, I didn't manage to prove that. I only proved the Cauchy's integral formula, so I will talk about it. And there's like thousands of lines about the code, so I don't go through the line by the line. I just tell you the basic idea. And there's something missing in the MathLib, like the definition of control integral for a general control. Actually, MathLib has definition for the circle integral, but it doesn't have the integral for a general control. Also, MathLib has the Cauchy's integral formula for a circle, but not for a general curve. For example, for this analytic theorem, we need the rectangle curve. So what I did is the first part plus the second part for rectangular path, which is sufficient to prove the analytic theorem. So let's talk about the first part. We need some preparation work. Let's see the code. To begin with, let's briefly introduce the files. What I'm working on includes 3 files. The first file is, can you see the code? Yeah, okay. So the first file is 2mathlib.lin. It consists of the basic lemmas that I want to put into the link. I want to put it into the MathLib. And the second file is control integral.lin, which corresponds to the first part of defining the control integral. And the third file is the rectangle and Cauchy theorem.lin, which corresponds to the second part of Cauchy's integral formula. So let's see the first part. For the preparation work, we just need some type conversions, like, there are like different products and satisfy some rules. I will skip that part. Also, some parts about affine function. Affine function is just of the form b plus k times t. And we need to establish the continuity and the differentiability of it and compute the derivative of it. And yes, the most important lemma in this part is the application of the chain rule. And also the definition of the path. So actually, I didn't define the path on Ling. I just regard the path as a function from R to C. Actually, a path is a continuous function from the interval 0, 1 to C. But the type of from the interval to C is not convenient to use in Ling. So my philosophy is that I just make the type as R to C, and we just ignore everything outside 0, 1. That's easier to manipulate. And we didn't define the path, but the operations of the path, like the constant path, we just assign every t to a single complex point. Also, the path concatenation, which is given by this expression, which is a standard definition. Also, the inverse of the path, which is parameterized by 1 minus t. So that's a basic definition of the path operations, and also some dumb lemmas about path operations. Like there are some important ones, like the image of the concatenated path is the union of them. It's quite long, but it's just a case-by-case discussion. And it's not difficult, actually. And also, we need some continuity of the path. Like if L1, L2 is continuous, and the concatenated path is also continuous. Yes, that's also the differentiability of the path. That's the preparation work. So let's go back to the definition of the control integral. So the control integral is defined to be a real integral. Here I want to make some comments. So first of all, the setup is general. I mean, here f is a function, right? Its domain is C, but its codomain, yeah, its codomain must be also C, right? But for generality, I set the codomain to be a general normed vector space. So L prime t is a complex number given a fixed t. So actually, it's a complex number scalar product with an element in the normed vector space E. So this is a scalar product. And secondly, here the L prime is derived L in Ling, and you know, we normally assume that the path is piecewise continuously differentiable. And actually, what if L is not differentiable? Actually, in Ling, if L is not differentiable, then derived L is assumed to be 0. So we can ignore this difficulty. And to define the integral, I don't only define the integral itself, but also the integrability. So let's see the code. So first of all, I define the control integrable, which is just to set this function to be interval integrable with respect to this measure. And we just establish some basic lemmas. And actually, the most difficult part is to prove the integral of the sum is the sum of the integral. It's quite surprising because it is not difficult in the sense of mathematics, but it's actually difficult to prove on Lie. So why is that? First, we have to clarify this. If f and g are both control integrable, then it is easy to prove that the sum of the integral is the integral of the sum. Because the definition is actually real integral, isn't it? So for the real integral, we have a lemma for this version in MathLib, so we can apply it. But the difficult part is that we have to connect the continuity of the function and the path to the integrability. So that's the important, that's the difficult part. Also, the change of a variable formula is also difficult. So here I listed some important lemmas in MathLib. The second and the third one is in the MathLib. The first one is not, but actually someone did it before. I found it in a Zulip chat. So I also applied it. And I can share the statement of these theorems. So this is the final version of this theorem. So the assumption is that f is continuous on both of the paths, and the path itself is continuous, and the derivative of the path is integrable on 0, 1. So given this hypothesis, we can show that the sum of the integral is the integral of the sum. Yes. So that's basically the first part. The second part is, as I said, is a Cauchy's integral formula for a general curve. We also need some preparation works about continuity and differentiability of some basic functions and definitions, properties of rectangles. Also, we need to turn the control integral along a rectangle into the real integral. So due to the time issue, I won't show you the code. It's not difficult, but it just needs dirty work. And we can formalize the Cauchy's integral formula in this form. So to prove this, we apply this technique. So we construct a new function gz to be this form. If z is not equal to c, z is just a slope. Otherwise, we define it as a derivative. So we have 3 steps. The first step is to show that g is continuous on the boundary of the rectangle and holomorphic in the interior of it. And secondly, we show that the integral of this function is 0 along the rectangular path. So as you can see, if the integral is 0, so we can move this term to the right-hand side of the equality. So the integral of fz over z minus c is equal to the fc over z minus c, right? Also the integral. And we can also put the FC outside of the integral. So finally, we have to show that the integral of 1 over z minus c along the rectangle is 2 pi I, which is the 1D number of the rectangle. And the first and second part is not too difficult because we have this and this in MATLAB. We can use it to prove the first two parts. But the third part is a little bit difficult. So my strategy is to split into 4 pieces. You know, the rectangle has 4 pieces, bottom, top, right, and left. And we compute the integral on each piece. So you can see all the terms are canceled out except the integral of the left side, which gives 2 pi I. So why is that? Because, you know, that corresponds to the branch cut of the logarithm. You know, there's a branch cut of the logarithm. So that gives 2 pi here. So the computation of the left one is extremely hard because it involves the discontinuity of the logarithm. So we still need to split it into 2 parts, the upper one and the lower one. What I need is the support of logarithm near the branch cut, which has a good support in MATLAB for this function. And secondly, I have to carefully distinguish the concepts of continuous and differentiable on and within that. So in line, so continuous on is the function continuous on the region. Continuous at is at a single point. Within that is continuous at a point within some region. So it's also essential to distinguish those 3 parts. Let's show some codes. So here, so first to define the rectangle, I have to first define the line segment, which is a function from R to C as before, of this form, which is reasonable. And we have to establish the derivative and continuity, differentiability of the line segment. And now we can define the rectangle path, which just joining those 3 pieces of line segments. So we define the bottom, right, top, left, and joining together to get the definition of the rectangle. And we need some lemmas about the rectangles, especially for the topological properties, like the interior of it is open, something like that. And also to turn the integral along the rectangle to a real integral, we also need some lemmas, like this lemma is very fundamental. So like if we rotate a path, then how does the contour integral change? So this lemma tells us the answer. And we can use this lemma to turn the contour integral along a line segment into a real integral. So then we can express the integral along the rectangle, which is stated as this. So the integral of the function along rectangle is the sum of these 4 parts. And then then we can formalize the Cauchy theorem on rectangles, which is an application of the Cauchy theorem in Lie. So a holomorphic function along a rectangular path is 0. And then we can formalize the Cauchy integral formula on rectangles. So as I said before, there are 3 steps. The first step is to deal with the slope, which corresponds to the d-slope function in MATLAB. And then we have to compute the 1D number of the rectangle, which is 2 pi I, and I split it into 4 pieces. So this is the top, the right, also the bottom. These are easy parts, but also need some proof. Actually, I have to deal with like the change of variable or chain rules formulas, something like that. Finally, for the most difficult part, I have to deal with the left piece. So the final statement is stated as this. So the Cauchy integral formula for rectangle, under the hypothesis of the continuity of the function on the boundary and the differentiability of the function in the interior, we have the Cauchy integral formula. So this provides a solid foundation for the analytic theorem, but I don't have time to prove it. But at least we have the Cauchy integral formula on rectangle, isn't it? So it's also quite nice, I think. And that's my work. And do you guys have any questions?
Thank you very much, both of you. That was great.